a radial part and an angular part. And we assume that our potential energy was central, only depended upon the distance from the origin. So we left the radial part here, 1 over capital R, partial R. Since it's just the radial part, I can also put a d by dr, r squared, partial r over small r, plus 2n over h bar squared, r squared, e minus vr, and we call this constant L e to L plus 1, right? Where L is some number. We don't know what that number is. Anyway, so this equation was solved in the recitation for a particular potential energy function, right? For the potential energy function for an electron inside the hydrogen atom. Now, the other part, angular part that I would like to talk about today is the following: 1 over y sin theta. Let's call it, okay, still let's not call it d, let's call it partial theta, sin theta, partial y, partial theta, plus 1 over y sin square theta, partial square capital Y, partial phi square. This must equal minus L e to L plus 1. Correct? Now this is the angular part of the wave function.
Did you derive it?
Yes, we derived it at the end of the last class. Alright, now how do we solve this equation? This capital Y is a function of theta and phi, whereas capital R is just a function of small r. So we've separated out the radial part and the angular part. And this separation could be achieved only because of the fact that the potential is central. It does not depend upon theta or phi. And this also shows that the Hamiltonian is invariant under rotations. And this is something we'll explore in the next lecture. Anyway, this y is now a function of theta and phi. Let's make an attempt of separating out the polar part from the azimuthal part. That is, let's attempt at factorizing out this function as a product of capital theta, which is only a function of theta, small theta, and capital phi, which is only a function of small phi. Let's make this attempt. That's why I call it an attempt or a try. Now, first of all, this is the angular part of the equation. This is some constant with the minus sign because both of these add up to 0. I would like to multiply both sides by y sin square theta. So if I do the multiplication, I am left, this goes away, a sin theta comes here, right, and a y sin square theta appears here. Now if I write y as a product of capital theta and phi, the left hand side simply becomes, now I am taking the derivative of y with respect to theta. There is no derivative with respect to phi, so I am left with a phi here, phi. Phi into sin theta, I call this d by d theta, sin theta, d capital phi by d theta. Right? This is the first term. The second term turns out to be capital theta d square by d phi square equals minus L plus 1 capital theta capital phi sin square theta. Correct? I've just replaced capital Y by capital theta into capital phi. Now I would like to divide both sides by y, by theta into phi. So how does this come? Because this partial y over partial theta is partial theta phi. So this phi is a constant, so it just comes out. It's here. Now I divide both sides by capital Y. And of course there is a phi square. Phi here. I divide both sides by theta into phi or by phi. This goes away. I'm left with a 1 over phi here. And I'm left with the 1 over capital theta here. So I just gathered this term and this term. One over capital theta sine theta d by d theta sine theta d capital theta over d theta plus m into L plus 1 sine squared theta plus 1 over capital phi d square capital phi by d phi square equals 0. So this is the angular part of the Schrodinger in the position representation. Okay, for central potential. Now there are two kinds of terms here. One is a term that only depends upon theta. This is theta dependent. Whereas this term is phi dependent. And both of them are identical to 0. So each one of these must be equal to a constant. Okay? So let's call this constant, this equals ml squared. Now I have no knowledge about what is small and what is small m sub l. I have no knowledge about these numbers. I am just presenting them as constants. And later we will find out what are the constraints of these constants. Okay. So let's look at, so this is called the azimuthal part of the equation. So the azimuthal part is quite easy to solve. So if I just take the azimuthal part of the equation, my d squared capital phi over d phi squared equals ml squared capital phi. Okay, so what's the solution for this equation? Phi, which is a function of small phi, equals some constant. Let's ignore the constant for the time being. It's normal efficient constant. I'm ignoring that. This capital phi equals e raised to power plus minus iota ml small phi. Okay, there's a plus and a minus sign here. I'm just taking the plus sign here. If I'm just taking the plus sign here, I'm assuming no constraint on the value of ml. It can be positive or negative. So I'm just taking the positive root. So this is a solution of the azimuthal part. The azimuthal part of the wave function. This is of course in the position representation. Right? It is a part of the wave function. The total wave function that we are seeking, psi, in the position space, which is simply this, has been proposed to be a product of a radial part and an angular part. And this angular part has been proposed to be a product of a polar part and an azimuthal part. So what we've done is we've found out a possible form for the azimuthal part. And I'm not putting in a normalization constant as yet because I can put it with this or with this. So this is the azimuthal part of the solution.
Sir, अभी तक m जो है complex हो सकता है?
mn कुछ भी हो सकता है, ठीक है। अभी हमने किसी तरीके का कोई इस पे constraint नहीं डाला. Now we will put a constraint. There are certain properties the wave function has to satisfy. First of all, it should be unique. Now this angle phi can vary and its principal value can lie between 0 and 2 pi. Okay, which means that if I draw the three-dimensional axis x, y and z, if I take a point which has an azimuth angle phi and the wave function has a certain value at this point, if I keep theta constant and I keep r constant and I rotate this wave function by 2 pi or multiples of 2 pi, the wave function must not change. The wave function must be single value. It must have a unique value at one particular value of phi. Right? So what does this mean? This means that if I take the wave function at multiples of 2 pi, the wave function should be equal to the original wave function. So this is my constraint. Right? The wave function cannot take up two different values at the same point in space. So if I look at the left hand side, this is E I M L phi E I M L n 2 pi equals E I M L phi. Remember, this n is an integer. Okay. Now, if this condition is to be satisfied, then this means that ml into n into 2 pi must be what does this, all of this this should be a multiple of 2 pi. Right? This should be some multiple of 2 pi. Okay? And it must also hold if n equals 1. Right? This, if it holds for any value of n, it must also hold for n equals 1. If it holds for any integer, it must hold for n equals 1. Which means that ml into 2 pi, I take this n equals 1, I can put some other integer k here and 2 pi here. Okay? So what does this mean? This ml is some integer. So I put a constraint on the value of ml by invoking the uniqueness of the wave function, the single valueness of the wave function, which means that this ml that I have defined, if this is indeed a mathematical solution, but if it has to be a physical solution as well, then this ml can only take up integer values. So ml can be 0, it can be plus minus 1, plus minus 2, plus minus 3, and so on. So we've solved the azimuthal part of the wave function. Now ml turns out to be a quantum number. It's called the azimuthal quantum number, and later we'll recognize what is the significance of this quantum number. Ali, sir, आप projector on करते हैं? पहले वहाँ से नीचे करते. Okay, now what I would like to do, once I found out the azimuthal part of the wave function, I would like to explore how do we solve this polar part. And since it's a complicated long derivation, I actually typed this up so that I can show it on screen. And I also uploaded this.
Why are we putting n is equal to 1 here? What if we put something else.
So it holds for every value of n, any integral value of n. So it must also hold for n equals 1. So if I put n equals 1, then ml into 2 pi must equal some multiple of 2 pi. Right? Which will tell us that
It will not
ml
be
is
an
an
integer
integer.
if n is something other than 1.
It would still be hold. It will still hold then. If n
Is something else but 1.
this is the at least the minimum requirement. This is what it must be. And if this holds true, then this will also hold true for any integer of n. But if this doesn't hold true, then this will never hold. Okay. So this is a necessary and a sufficient condition for this to hold. The converse may not be true. Because if I put an integer k into 2 pi here, then this 2 pi cancels out and then turns out to be k over n, which is not necessarily an integer. Right? But this must hold, the strictest condition that when this holds is when n equals 1. Okay. That's why ml into 2 pi is equal to k into 2 pi ml turns out to be equal to k. Okay? I hope I have described your confusion. Clarified. Alright. Now we would like to solve the angular part, just the polar part. We solved one part of the angular part, the azimuthal part. Now we're going to solve the polar part. Polar part is the theta dependent part. Alright. Now we've already gone through all of this. We solved the azimuthal part. Now we would like to solve the polar equation, right? Now this polar equation is simply this part, and this part must equal minus ml squared. So if you observe,
Shouldn't it be equal to n squared times 5
दोनों साइड्स को कैपिटल थीटा से मल्टीप्लाई करके साइन स्क्वायर थीटा से डिवाइड कर देंगे आगे। देखिए दोनों साइड्स को कैपिटल थीटा से पहले मल्टीप्लाई करें और साइन स्क्वायर थीटा से डिवाइड करें, तो हमारा ये चीज आ जाएगी। Sorry.
So shouldn't this be equal to alpha squared? Negative alpha.
यहाँ पे मैंने एक to simplify matters, let's put this equal to minus ml squared, right? If I put this equal to minus ml squared, this will still be a solution, right? If I put this equal to minus ml squared, I can put this equal to plus ml squared, right? Okay, I can do it either way, but my solution conforms to calling this plus ml squared. Okay. अब ये समझ आइए ये क्यों प्लस साइन का स्क्वायर?
सर दोनों का कांस्टेंट सेम रहता है ना,
एक प्लस होगा एक नेगेटिव होगा ना, दोनों को ऐड करके 0 लाएंगे. ठीक है, दिस इज प्लस साइन का स्क्वायर. नाउ आई हैव दिस पोलर इक्वेशन. Let me write down this polar equation. Or do you want me to go directly here? It's quite straightforward. It's very straightforward. Okay, so this is the polar equation here. Okay, and this conforms to the result over there. Now I multiply this equation by capital theta. Right? I multiply this by capital theta, I get this form. I've just done some algebra. I take L plus 1 to the other side. Now I multiply by sine square theta. So I remove all the denominators. This is what I get. Okay. Now I perform a substitution. I call cosine theta z. This means that sine square theta is 1 minus z square. Sine theta is this under root. dz over d theta will be minus sine theta. So I am just replacing the variable theta by z. In other words, I am trying to replace trigonometric functions by algebraic functions. Okay. Now suppose the solution that I am seeking, the polar part capital theta as a function of theta is some p which is a function of z. Okay, because I changed the variables from theta to z, my solution is now a function of z. Let's call that solution p. Okay. Now, okay. My original equation, this equation also has derivatives of theta with respect to small theta. But I would like to replace all the capital thetas by p and the small thetas by z. So I would like to express this d capital theta over d theta by in terms of dp over dz and z. So I use the chain rule. This is what I get. This means that dp over dz is equal to this. So I have expressed my d theta over d theta in terms of dp over dz. But my original equation also has a double derivative. D square capital theta over d small theta square. So I would like to find out how does this map in terms of p and z. So this is equal to this. I've already found out what is d capital theta over dz. I put this in here. Okay, then I use chain rule here again. Fine. So this is what I get. dz over d theta is minus sine theta. And then I just carry out the differentiation. This using the product formula. This is what I will get at the end. This is the double derivative of capital theta with respect to small theta. Now I would like to replace the sine thetas wherever I am seeing a theta by a z function of z. Sine theta I know is equal to this d, and this function, this d derivative of sine theta with respect to z is actually the derivative of the square root with respect to z, and it comes out as this. Thus, with my double derivative can be solely expressed in terms of p's and g's. Now I have a double derivative and my single derivative all expressed in terms of z's. Sine theta, cosine theta, everything expressed in terms of z's and p's. Therefore my polar equation takes up this form. Okay, so I have converted from the trigonometric polar coordinates to the algebraic coordinates. Okay. And remember that my z is equal to cosine theta. So if my theta goes from 0 to pi, my z, the range of z is from -1 to +1. So I've changed the domain of my problem as well. Now I have this polar equation. I just do some multiplications, gather terms together, divide by certain terms, and this is the final equation that I get. And this equation is called the Legendre equation. Probably you studied it in mathematical physics, but it's one of the most important equations classical physics. Okay. Now I would like to, so the problem of finding the angular part of the wave function is converted to the problem of finding the solution to the Legendre equation. So this is the Legendre equation. Okay. Now how do I solve this equation? There are different ways of solving this equation. One is using a power series solution. I propose that this PZ is a power series solution, which means that this PZ is equal to some GZ and a power series of 1 minus z square raised to power absolute value of ml divided by 2. This is a proposed solution. Okay. So we would like to perform this substitution. So we put in dp over dz. This, we perform the derivative of this function with respect to z. This is what we get. Now we do algebra. We multiply both sides by 1 minus z square. But because what we are interested in is we want to multiply this dp by dz by 1 minus z square. Okay, and this pz is already here. All the rest are ml and l's are constants. Okay, and z is the variable. So I find out 1 minus z square dp by dz. I take its derivative. Why do I take the derivative? I take the derivative because there is a derivative here as well, dp by dz. So there is a double derivative. So I would just like to put in all of these values in here. It's long algebra. It took us quite time to type this up. So this is only algebra. Only algebra.
So how much of this is algebra do we need to know? Like
I mean, you need to go through this once.
once?
Just once, but it's not difficult. You go through
It's not difficult, but the whole point is at some point you're like bored. You get lost somewhere and it's hard to recover.
So Legendre wasn't bored.
Actually, had many years to do this.
Okay, so this is the final equation that we get. So we convert it from theta to small theta to z. Capital theta goes to p. Now p has been expressed in a power series of g's. Okay, and this is the equation for g. Okay,
So what do you call it?
g is some associated function. Some associated function. Now this g is expressed as a power series of z's. Okay, suppose this gz equals z raised to power n and some coefficient where n goes from 0 to infinity. This is the power series solution method of a differential equation. You propose a power series as a solution and then you find out these coefficients in ans. Now we know this is gz, we find out the first derivative. This is the first derivative and then we find out the second derivative. Okay, and then we put these values of g's, g prime and g double prime into equation number 7. Right? So this is what happens after substitution. And equation 8 is the equation that we achieve. And the a's are the coefficients that we seek to determine. Now we notice a few things. The first parenthesis equals this particular function. The second parenthesis, this one, equals this particular summation. The third parenthesis equals this summation. And this last parenthesis equals this summation. Therefore, equation number 8 can be written compactly in this form. Now you notice that with each term there is a summation from n equals from 0 to infinity. Therefore, each of these terms for any n must equal 0. Therefore, if we just remove the summation signs, for each n this equation must be satisfied. Now this is a purely algebraic equation. And this is the solution that we finally achieve. And the solution is recursive. If I know an, I can find an plus 2. Okay. Alright, now let's look at this particular, what's inside the square brackets. Now notice that n was just some variable range from 0 to infinity. So n can take up any value. However, if we notice here, the argument inside the square bracket goes to 0 for a particular value of n. Let's call it n max. Now ml is fixed. For a particular value of ml and a particular value of L, we would like to find out what's n max. So this will go to 0 when n max plus ml into n max plus ml plus 1 equals this number, ll plus 1. Right? Now n is an integer, ml is also an integer. And you compare the left hand side with the right hand side. If n max is an integer, ml we already know is an integer because that's constrained. This means that this small l must be an integer. And it must be a positive integer. Because ml absolute value is positive. So we have put a constraint on l. Small l is an integer. It must be non-zero.
So why are we putting this absolute value of ml?
Because this was in our original trial solution. So now we have put a constraint on the value of small l just from solving the differential. ml पर पहले constraint आ चुकी है, small l पे भी constraint आ चुकी है. ठीक है? तो ये जो small l है, this must equal n max plus ml. And don't confuse this n max with the principal quantum number. So this Gz goes from 0 to n max. And this Pz, which is given by this number, Pz is equal to this, and this Pz equals to theta. Right? And how do we find these coefficients? We set some coefficient for one value of n, and then we find the other coefficients recursively. And we go up to the value of n max. And so you can look at a few examples. When L equals 0, ml equals 0, right? So we can find n max, we can find our solutions, right? So just go through these different cases, and it will help you find out the values of capital theta or p. And then if you combine these azimuthal wave functions with the polar wave functions, you get the spherical harmonic functions, which are the orbitals that you see in the hydrogen. Okay, so we'll continue this discussion on. So this document is uploaded. You should go through these calculations and convince yourself that these are the functions of it. You should do it once in your lifetime. Just once.
Even once before, like
Go through it once. Why are you so afraid of doing?
सर उसके बाद कभी करने की जरूरत थी.